Scientists may have finally solved the black hole information paradox. Source: Institute of Experimental Physics (SAS) research published in General Relativity and Gravitation. For nearly 50 years, one question has haunted modern physics. What happens to information that falls into a black hole? If you like my videos, subscribe my channel and press the bell icon to turn notifications on so you keep getting all the major advancements in science and technology. And don't forget to like and share this video with your friends and colleagues. Comments are welcome and open for discussion. At first, the answer seemed obvious. Nothing escapes a black hole. Whatever crosses the event horizon is gone forever. But in the 1970s, Stephen Hawking made a discovery that changed everything. Black holes, he showed, aren't completely black. They slowly leak energy through a phenomenon now known as Hawking radiation. Over unimaginably long periods of time, they gradually shrink and eventually disappear. That prediction created one of the greatest paradoxes in science. Because according to quantum mechanics, information can never truly be destroyed. So if a black hole completely evaporates, where does all the information go? Does it vanish forever? Or is something missing from our understanding of reality itself? Now, researchers have proposed a bold new solution. One that not only claims to solve the black hole information paradox, but may also explain why elementary particles have mass in the first place. If they're right, two of the biggest mysteries in modern physics may share the same hidden origin. To understand the paradox, we first need to understand what physicists mean by information. In everyday language, information means facts, memories, or data. But in physics, information refers to the complete description of a physical system. Every particle has properties: its position, its momentum, its electric charge, its quantum state, that. Together, these properties completely describe what that particle is. Quantum mechanics tells us something extraordinary. No matter what happens, that information can never simply disappear. It can change form, and it can become scrambled. It can spread throughout the universe, but it cannot be erased. This principle lies at the very heart of quantum theory. Now, imagine throwing an entire library into a black hole. Every book, every page, every letter, every atom. Once everything crosses the event horizon, the outside universe can no longer access any of it. That alone isn't necessarily a problem. The information is still inside the black hole, but Hawking's discovery changes the story. As black holes emit Hawking radiation, they slowly lose mass. Eventually, they disappear completely. And Hawking's calculations suggested something unsettling. The outgoing radiation appears completely random. It doesn't seem to carry any information about what originally fell inside. If that's true, then when the black hole finally evaporates, the information is gone forever. Quantum mechanics says that cannot happen. General relativity appears to say that it does. For decades, physicists have struggled to reconcile these two pillars of modern science. The new study approaches the problem from an entirely different direction. Instead of changing quantum mechanics, the researchers ask whether our understanding of gravity itself is incomplete. Einstein's general relativity describes gravity as the curvature of spacetime. Mass tells spacetime how to bend. Curved spacetime tells matter how to move. It is one of the most successful scientific theories ever developed. But another, lesser-known version of gravity exists. It's called Einstein-Cartan theory theologies. This theory keeps everything Einstein described while adding one entirely new ingredient: twisting. According to Einstein-Cartan theory, spacetime doesn't only bend. Under extreme conditions, it can also twist. Physicists call this twisting, torsion. Under ordinary conditions, torsion is so incredibly small that it becomes virtually impossible to detect. But near the enormous densities found inside black holes, the theory predicts that torsion could become extraordinarily important. The researchers push this idea even further. Instead of describing the universe with the familiar 3 dimensions of space and 1 dimension of time, their model introduces 7 dimensions. These additional dimensions aren't places we could travel to. They're hidden mathematical directions woven into the fabric of spacetime itself. Within this 7-dimensional geometry, torsion behaves in surprising ways. As matter becomes compressed toward unimaginable densities, the twisting of spacetime generates a new effect, a tiny repulsive force. Normally, gravity continually squeezes matter inward, but this new force pushes back. At everyday scales, it's completely negligible. Inside a dying black hole, it could become powerful enough to halt the final stage of collapse. That single prediction changes everything. Why? According to Hawking's original picture, a black hole eventually evaporates until nothing remains. The new model suggests something different. Instead of disappearing completely, the evaporation suddenly stops. A tiny remnant survives. This leftover object would be unimaginably small. Its predicted mass is only about 9 times 10 to the minus 41 kilograms, far smaller than anything we could directly observe today. Yet, despite its tiny size, it could preserve everything the black hole ever contained. That immediately raises another question. How can something so incredibly small store the information from an entire star? The answer lies in vibrations. When physicists study black holes, they often describe them as ringing after disturbances, much like a struck bell. These oscillations are called quasi-normal modes. The new theory proposes that the remnant continues supporting an enormous collection of these microscopic vibrations. But unlike an ordinary vibrating object, these oscillations exist within the twisted geometry of spacetime itself. The researchers argue that quantum information becomes encoded inside these long-lived vibration patterns. Nothing is destroyed. The information simply becomes hidden within the remnant's internal structure. According to their calculations, a remnant left behind by a black hole with the mass of our Sun could store roughly 1.5 times 10 to the 77th qubits of information. Remarkably, they calculate that's exactly enough to preserve every quantum detail that originally entered the black hole. If true, the information paradox disappears. Nothing was ever lost. It was simply stored in a place we hadn't considered. But the researchers didn't stop there. Their model also reaches into another of physics' greatest mysteries. Why do fundamental particles have mass? According to the standard model of particle physics, particles acquire mass through interactions with the Higgs field. This explanation has been enormously successful. The discovery of the Higgs boson in 2012 confirmed that the field exists. But physicists still don't fully understand why the Higgs field has precisely the strength that it does. The new theory proposes something unexpected. When the 7-dimensional geometry naturally reduces to the 4-dimensional universe we experience, it automatically produces the same energy scale associated with the Higgs field. In other words, the geometry responsible for preserving information inside black holes may also be responsible for giving elementary particles their mass. If that's correct, gravity, quantum information, and particle physics become connected through a single geometric framework. Naturally, this raises the biggest question of all. Can the theory actually be tested? The answer is yes. Well, perhaps. Unfortunately, the extra dimensions predicted by the model exist at energy scales enormously beyond today's particle accelerators. Even the Large Hadron Collider falls millions of times short of reaching those energies. But physics doesn't rely solely on particle accelerators. The universe itself often performs experiments far beyond anything humans can build. The researchers suggest several possible observational tests. One involves the remnants themselves. If countless ancient black holes left behind these tiny relics, they could contribute to the mysterious dark matter that appears to dominate much of the universe's mass. Another possibility involves gravitational waves. The unusual vibration patterns predicted by the theory may eventually leave detectable signatures, unlike any competing model. And because these enormous energies existed naturally during the earliest moments after the Big Bang, subtle traces of the seven-dimensional geometry might still be preserved inside the cosmic microwave background, the oldest light in the universe. Future observations may reveal whether those signatures exist. It's important to remember that this remains a theoretical proposal. No one has yet observed these remnants. No experiment has confirmed the existence of spacetime torsion or hidden seven-dimensional geometry. Many competing ideas also attempt to solve the black hole information paradox. Some suggest information escapes through Hawking radiation itself, others invoke holographic principles or entirely new quantum gravity theories. The debate is far from settled, but what makes this proposal especially fascinating is its ambition. Instead of solving just one mystery, it attempts to explain several of the deepest puzzles in physics using a single underlying principle. Perhaps that's how the next great breakthrough will happen, not through discovering an entirely new law of nature, but by realizing that mysteries we've treated as separate have been connected all along. Black holes, quantum information dots, dark matter, the Higgs field, extra dimensions. They may all be different pieces of the same cosmic puzzle. And if this new theory proves correct, the greatest secret hidden inside a black hole may not be what disappears forever. It may be the clue that finally reveals how the universe itself is built.